we now go ahead and substitute 1 plus KLT for e to the KLT, and we do this carefully. That gives us L times y naught divided by y naught multiplied by 1 plus KLT minus 1 plus L times e to the KLT. Now, this expression clearly simplifies. We end up with L times y naught divided by y naught plus L, and that's multiplied by e to the KLT, y naught times KLT plus L. Now, our assumption is that t is small. We can choose to make t small enough that y naught KLT, and let's write that out, make t small enough that y naught KLT is much less than L. And by much less, we'll see how much less we really want it to be when we see how this affects our approximation. So we can certainly choose to make t small enough, and it's small enough, not small enough. Maybe I can get rid of that t with a properly placed push pin. Maybe a little dangerous, but okay. We make t small enough that this is the case, so that we can then say that this denominator is just pretty much equal to L. If this is much less than L, then adding this to L does not significantly increase L, and we get then L y naught over, push pin might not have been a good idea. Let's try it like this. Okay. Again, this denominator is essentially L, so we effectively get something that's at least close to L times y naught over L e to the KLT, which is y naught e to the KLT. Now again, this is for small t. This expression is nothing but exponential growth. E to the KLT is just exponential growth with growth factor, growth rate KL. We'll see maybe how that's interpreted, but this confirms that for small populations, for populations much less than the limiting population, this population grows exponentially, as would a purely exponential model in which the population growth is proportional to the population. That is, the rate of change of the population is proportional to population. So we say rate of change of y is proportional to y. That would be a solution to the equation y prime equals KL times y.